Hello, my name is Kevin, and today I'm being joined by Lara, Darren, and Zach, and we're going to be talking about food coloring. Now, food dyes are important because they are used in almost everything we eat. They have a long history, and most importantly, all food dyes are organic molecules.
A molecule will take on the color of whatever visible light it does not absorb. For example, if we have these four lights traveling toward this transparent orange block, only yellow and red will be able to pass through, as yellow and red combine to make orange. Something most colored organic molecules share in common is conjugation. For example, here on the left, this sp3 carbon blocks conjugation, but if we add an OH-, this sp2 carbon allows for conjugation, and this does have a color.
It's springtime in the Midwest, which means flowers, random snow showers, and Easter eggs. Now this video is a little late for Easter, but it's never too late for science. This experiment will show 4 different ways to dye eggs and reveal the science behind it. 2 eggs will have vinegar. Many recipes call for putting vinegar in the water with the eggs when dyeing them. This is because vinegar has acetic acid, which dissolves the eggshell and protonates the cuticle underneath. The positive charges then attract the negatively charged dye, which makes the colors stick to the egg better to produce brighter colors. This reaction also produces carbon dioxide gas, which is why the eggs bubble when you put them in vinegar. 2 eggs will have artificial dyes, and 2 will use a natural dye. This experiment will compare good old McCormick food dye to beet juice. The artificial dyes contain water, propylene glycol, propylparaben, and the various F, D, and C colors used to make red, yellow, green, and blue dyes. They are very popular for egg dyeing because they provide such vibrant colors, which makes the kids happy dyeing them and the parents concerned about staining. Beets are also approved for food color additives because they contain betanin and stain like nothing else. If you think I'm kidding, grab some beets the next time you go to a salad bar, which will be a while because we're in a pandemic, and see how they turn your plate into a possible murder scene. Betanin is a red glycosidic food dye, which means it has a sugar, glucose, bonded to a functional group, betanidin, via a glycosidic bond. It's used regularly in a variety of foods, from soft drinks to ice cream. So now that we've discussed the science behind the experiment, let's jump right into it and see how the eggs will look depending on what we put them in. We have to prepare the eggs, of course, boil them until cooked. Adult supervision is probably smart, even if you're almost 20, and especially if you have to ask your mother how to cook eggs in the first place. That's really hot. Oh no!
What?
One of my eggs cracked!
I told you should have done 6.
Yeah, so listen to them if they know what they're doing. While the eggs are boiling, prepare the beets. The ones here were pre-cooked, so I just blended them into a puree and put them in a skillet with some water. Heating up the mixture caused the water to hold the betanin, which you can see was a deep red color. You need enough to cover 2 whole eggs, which is about 1 cup. The more water you leave, the more transparent the juice will be, so try to use as little as possible to get a darker color. The artificial dye mixture is easier to make. Add drops of dye to 1 cup of water until you're satisfied with the color. Try to match the color of the beet juice to better compare between the 2 options. Then put the eggs into the cups and add the liquids. I put 1/4 cup of dye into each cup, 2 with the food coloring, 2 with the beet juice. Then 2 eggs got 1/4 cup of vinegar, and 2 got 1/4 cup of water. A side note while we wet on the eggs, you can actually make brownies with beets. These will make the brownies more moist and will use up the beet puree that you had from making juice. They were actually pretty good and you didn't taste the beets at all, and baking is chemistry. I let the eggs sit for about an hour and 15 minutes. I was going to do 2, but then that happened, so I decided to take them out. Each egg had some sort of coloration on it. The water artificial combo was the prettiest pink. The water beet combo was the least amount of color. The vinegar artificial combo was brown with how much dye stuck to it, and the vinegar beet combo was a little darker pink. Clearly, the 2 eggs with vinegar were the darkest. This is what we expected, since the acid dissolved the eggshell and used protonation to attract the dye to the egg, making the color deeper. You can even see the spots where the carbon dioxide bubbles were in the way of the dye. The 2 beet juice ones were lighter in color. This makes sense. The dyes are stronger chemicals than betanin and are more likely to rearrange the molecules on the egg so they absorb different colors. For this reason, artificial dyes are often used over natural ones. The colors just look better and last longer. So that's the end of the experiment, but the science doesn't have to end. Go ahead and try this on your own.
The first evidence of food coloring comes from ancient Egypt, where paintings as old as 1500 BC depict the coloring of candy. In 300 BC, ancient Egyptians colored wine by leaving the grape skins in contact with the juice after pressing, turning the clear juice red via the transfer of the anthocyanins myrtillene, chrysanthemine, and oanine. Natural pigments have been used very commonly throughout human history. Carmine, a crimson-colored dye produced from cochineal insects, was used in early American history by Aztecs and Mayans as a rare commodity. Once discovered by Europe, carmine was used mostly in the textile industry, but was also often used to dye various fruits and beverages. Another example is crocin, found in the expensive spice saffron, which has been used to color food due to the rich orange color it gives off at higher concentrations. Before the crocin comes quercetin, an insoluble carboxylic acid which must undergo esterification with genteel biosugar in order to become the soluble crocin. So here, the mechanism of this is that a proton is grabbed by this insoluble. It's insoluble because of carboxylic acid, and long-chain carboxylic acids are insoluble in water. So it grabs a proton, then genteel biosugar attacks. Then here we have proton transfer within the molecule, and a good leaving group is formed. The leaving group leaves, and this bond here becomes double, and this proton leaves, and it happens again on this carboxylic acid, forming alpha-crocin, which is water-soluble. So, as science advanced, natural dyes were eventually replaced by their cheaper, longer-lasting, and better-looking alternative synthetic dyes. The synthesis of the first artificial food dye occurred in 1856, when William Henry Perkin accidentally discovered moibine, a mixture of 4 related aromatic compounds, while looking to cure malaria. Here we can see that the 4 compounds differ by the placement and number of methyl groups. Additional dyes were synthesized afterwards and mass-produced. By 1860, 4 years later, the French were dyeing their wines with fuchsin. The United States would legalize the use of synthetic organic dyes in butter in 1886. The development of cheap food further encouraged the growth of the food dye industry, as natural dyes could not be produced at the cost and quantity necessary to keep up with the food being made. By the 20th century, synthetic food dyes were a part of daily life in the U.S. With this growth, synthetic dyes eventually came under criticism. Coloring would often be added to conceal defects and grime. For example, pasta noodles were dyed yellow to conceal dirt. More dangerous food additives included lead chromate, copper sulfate, and red lead, additives that ended up killing many people. Today, many more regulations are in place to help keep our food safe, since the Pure Food and Drug Act in 1906. The past 20 years have seen a shift from artificial to natural, and there is much debate over which is preferable.
As mentioned earlier, there is still a lot of debate between natural and unnatural dyes. One manifestation of this debate occurred in around 2015, when major food manufacturer General Mills decided to change the recipe of Trix breakfast cereal to use natural dyes instead of artificial ones. Here you can see a list of some common artificial dyes, almost all of which were used in the original recipe for Trix. The natural dyes used as replacements came from many sources, such as these ones listed here. The problem General Mills ran into was that they could not achieve the same intensity of color without impacting the taste of the cereal. This was especially true with the orange color, which came from carrots. Eventually they decided to prioritize flavor over color, leading to the release of a bland-looking cereal that was not well received. Due to public outcry, General Mills decided to sell old Trix again, along with the natural Trix. But as natural Trix continued to underperform, it was eventually pulled from shelves. This flop led to a massive halt in the transition to natural dyes in the industry, and shows how impactful the color of food is to the consumer.
There have been many claims about the possible dangers of artificial food colorings. The most common of these claims are that food colorings can cause allergies, increase hyperactivity, and even ADHD in children, as well as increasing the rate of cancer growth. Many of these claims are highly contested, and studies have concluded mixed results overall. However, that does not stop articles like the ones shown being written and scaring the common people. There are 6 artificial dyes approved by the FDA and the European Food Safety Authority, or the EFSA. These dyes are red 3, red 40, yellow 5, yellow 6, blue 1, and blue 2. Many of these dyes were used in combination with each other to make the artificial dye used in our experiment. Some dyes, like green 3, which is not shown here, are approved by the FDA for use in the US, but not by the EFSA for use in Europe. As mentioned previously, the studies performed on food coloring have few conclusions. Red 3 has shown a link to increased thyroid cancer when tested on rats, but no other dyes have a conclusive link to cancer. However, some known cancer-causing agents can be present in some dyes as a contaminant. These contaminants are present in very low levels and are therefore presumed to be safe. There has also been a small but significant link found between food dyes and hyperactivity in children. In conclusion, there are very few studies that have a significant result regarding the safety of food dyes. We do know that artificial dyes are often used in highly processed and unhealthy foods like candy, lollipops, and macarons. In order to avoid dangers that food coloring may present, cut back on the candy.